Ryan.
Oh, okay.
There it goes.
The recording has started.
Let's
go ahead and get started. My name is Rosa Ornstein. I'm chair of the North Texas Renewable Energy Group this year. I want to welcome both new people who have never joined us before and our returning members and guests who are regular participants in our monthly membership meetings. As you know, we try to bring in speakers of note that will help educate the public as a whole on renewable energy and sustainability. And I know personally, Gary Olp has been on my radar to bring to speak to our group for quite a while. Before we get started though, we do have a few business matters that we take care of every month with our membership. And the first of those updates that we need to give the membership has to do with our 2021 community project that we selected this year. It's our inaugural year to undertake a project for the community that brings to bear the incredible skills and experience and expertise that reside within the group. So Michael, let me turn it over to you, please.
Hi, everyone. Thank you for the opportunity to give you an update report on our what we call the Dallas-CIC team, where we're supporting the City of Dallas's CCAP initiative. And we had we started the program, or as far as our deliverables, a little over a month ago. We had a very short window to provide a questionnaire to help the city staff select their facilities, but it can be stepped out from there, of what is being referred to as a resilience hub, which is a facility that can be maintained off-grid for 3 days, 72 hours, and support 100 people. And so we submitted that at the end of June. We've had some going back and forth with some revisions since then. So our final document is actually this week. We have a presentation to the City of Dallas and their city staff on that program in 2 weeks. And then hopefully it will be available for public comment and review at that time as well. Then we have a second program, a deliverable for the city. And this is focused on what's being referred to as renewable energy hubs. And we're going to be conducting research and evaluation, trying to define exactly what a renewable energy hub is, and coming up with a guideline to be able to, all the components and moving parts for the city to use to be able to evaluate locations for making that happen. And so that's due August 31st, and we'll be giving you an update report after we get that submitted as well. So I turn it back to Rosa. Thank you.
Thank you, Michael. And just so that everybody here.
Can I say one thing? I just want to make,
yes,
I want to thank the team that stepped up to the plate and volunteered. I'm going to, we worked with the city staff, Susan Alvarez and Katie Evans, and then Pete Parsons, which is our Texas executive director. She participated quite a bit. Rosa, of course, Benjamin Wang is a member, comes from the industry. Dan Lipinski, technical support and a member. James Orenstein, a member. Molly Rook, a member. And Mark Woody, a member. This couldn't have been accomplished with all their contributions. We appreciate it very much.
Thank you, Michael. And that will segue quite nicely into what I was going to say. We still need volunteers for this project, especially for the renewable energy hub that we will have to develop again a questionnaire and a rubric for how you select and create a renewable energy hub. So any member or any person who is on this call, is welcome to contact anybody on the board, and in particular Michael, since he's spearheading the community project this year. And please come and participate. We need your help. We would greatly welcome any participation from anybody to help us move that project forward. Another update we have is last year we started working with the Texas Solar Energy Society to help develop an internship program. As you all know, the industry, the renewable energy industry, the solar industry is not a very diverse group. And there have been efforts made to diversify both gender, ethnic, and racially the composition of the industry. In that context, Texas obtained a grant from the Meadows Foundation last year to help develop an internship program to help diversify the industry. And this year, we are the recipients of a $10,000 grant from the Texas Solar Energy Society for us to put forward and carry out an internship program in the North Texas area. Lisa Magel, Ryan Clements, and myself have been working on that quite assiduously with the executive director of the Texas Solar Energy Society, Pete Parsons. We have substantially completed the application form. We've identified solar and renewable energy companies that could employ some of these interns. We've started creating the list of schools to contact so that we can make the internship opportunity known and available to students in the North Texas area, in the colleges in the North Texas area. And we wanted to let you know we're also doing that this year. And I welcome again participation from the membership and from people on this call who may be interested in helping, whether it's helping carry out the program or publicize it, or know of, for example, technical schools that we might want to contact their people to publicize the opportunity, or to renewable energy companies that might be interested in hiring an intern. We will be using some of the funds that we are getting from Texas to help subsidize the payment that will be made to the interns. We also need mentors, because each intern will have a mentor from outside the company they're working on, so that they can feel free to express any concerns, challenges, and praise also that may be going on during their internship. So this is a call. I need mentors and I need volunteers to help us as well. So please contact me. My contact is on the NTREG website, and I will make sure that you get involved and become part of the team to help us carry this forward. Lisa, could you give us an update on membership, please?
Hi, I'm Lisa Magel. I'm the membership coordinator for NTREG, and I want to welcome all our regular members who are attending today and new people. NTREG meetings are always free and open to the public. I mean, our goal is to educate anybody and everybody about energy efficiency and renewable energy. But that being said, there are some costs that we incur for our Zoom subscription these days, where we have remote meetings. The really cool thing about remote meetings is we can get speakers like we had, remote speakers like we had last month, Amory Levins from out of state. But we also had to up the price of our subscription for a month, because we had almost 100 people at last month's meeting. So membership in NTREG is only $20 a year. You can join via the NTREG website, or you can also go to our mothership, the Texas Solar Energy website, txses.org. And then of course, our website is ntreg.org. You can join on either place, and we'd very much appreciate it if you do. If you become a member, you get to officially run for office if you want to. We'll be having elections coming up probably in January, and you can vote, which, you know, we all know voting is important everywhere. So anyway, again, if you're curious about your membership status, you can send me a message in the chat and I can look you up and say if you're current or when you are up for renewable. But again, welcome to everybody, and glad to see you. Thanks.
Thank you, Lisa. Mark, I know you're traveling. I didn't know if you wanted to make a short update to the group, especially on the DFW Solar Tour status. I may have lost Mark Whitty. As you know, the Solar Tour is our signature event for NTREG and has been. I think we've done it for 11 years in a row. At one point, we were the largest solar tour in the country. It's usually the first weekend in October. We are always needing volunteers, especially because this year, well, last year was all virtual because of the pandemic. We're exploring to see if some of the DFW Solar Tour this year can be in person so people can get back partially to the touchy-feely and actually see the systems that are installed in person. But we need volunteers to help Mark Whitty with that. I know he put out a call and we will be reaching out individually to people who have helped us in the past. We also need hosts, which we've had in the past as well. So I think we lost Mark, but I wanted to make sure that everybody knew that we're working on the DFW Solar Tour, which is our signature event. And we need your participation with that as well. We're also trying to educate the public by having Solar 101 presentations to different organizations throughout the year. And if you know of an organization that would like to have a presentation made by one of our presenters from NTREG, we've got a number of people that do that, that are members of NTREG, and we would welcome making those presentations. We're just trying to educate the public as much as possible. So thank you very much, everybody, again, for being here. We also have, during our membership meetings, an opportunity for members, guests, and other groups that we affiliate with to make announcements of renewable energy or solar, wind, sustainable events or matters that are going on that they think is important for the group to know. So are there any members on the call that have any announcements that they wish to make? If you so, just unmute yourself and make the announcement, please. Anybody? Okay. How about any guests that are attending today? Any announcements they wish to make? Okay, I don't hear anybody piping up. The Climate Reality Project is a group that we try to work in collaboration with as much as possible. Their membership meetings are the third Saturday, which is next Saturday of the month, and they meet from 1 to 3 p.m. We have their website on this introductory page agenda here, so that you can go to their website if you want to start attending their meetings or participating with them. How about the young professionals in energy? Ryan, do you have any update on that? That group?
Hey, Rosa, no update at this time. Okay,
terrific. With that, Gary, we're going to jump right into your presentation. First of all, thank you so very much for being here. Normally, Joella Phillip would do the presentation since she and Gregory Isaacs are programs co-coordinators. Since I invited you and you had been on my list for quite a while to get you to us, I thought I would take a point of personal privilege and welcome you to NTREG. Most or a lot of people on this call know Gary, and some of them I'm sure have known Gary much longer than I have. Gary is a fellow of the American Institute of Architects and an LEED fellow as well. You also, for those of you who joined early, heard about his participation as well with the Solar Decathlon. He directs the GGOArchitects, Inc. It's an acclaimed architectural studio in Dallas, Texas, dedicated to excellence in design and sensitivity to place and the environment. They were the first green practice to open in Dallas, focusing on green buildings that incorporate efficiency, energy, passive solar techniques, non-toxic materials. Gary has completed more than 350 projects, including residential, commercial, institutional, and museum work throughout the United States. He also serves as a board member on various cultural, educational, and civic boards and committees and task forces, including the nonprofit Sustainable Dallas organization in Dallas. Gary and his firm, GGOArchitects, have been and continue to be recognized as a leading sustainability-focused firm. And they've been recognized with 7 design awards, 3 energy value housing awards, multiple green building awards and honors. Gary also designed the very first LEED Platinum certified home in the state of Texas, the Heather's Home, which was featured in the Oprah magazine. Gary, we are proud and honored to have you be our speaker today. Thank you very much, and the warmest of welcomes to you.
Thank you, Rosa. Do I switch over to my screen now? Share my screen?
Yes, sir, please.
All right. And share. Here we are. Everybody can see the screen? Rosa, is it up?
Yes, sir.
Okay. Well, we'll open this presentation with just a little bit of disclosure. What I am not is a scientist, and what I am not is an engineer. I'm an architect. I've been practicing in this field for quite a while. I'm going to date myself, but I can share with you that in 1977 in Central Ohio, I built an earth-sheltered home that virtually heated itself. We used solar panels at that time that were rudimentary. In fact, they were constructed on site, working with some plumbers and so on. And the truth about that house is you had to be a master plumber to keep that system running. Those are in the very early days, and was influenced by people who were doing earth shelter, who were doing full earth covered buildings and so on. So that's what's happening here. I can't see my screen.
There's a break by Gary to fix his screen. Please send your questions to the chat box so that Gary can make his presentation. We can take breaks in between to answer the questions on the chat box as well. If you're not speaking, please mute your phone so that we keep down the background noise and we can all enjoy Gary's presentation. Thank you.
Okay, Rosa, can you see, everyone can see the screen?
Yes, sir.
Good. So as I was saying, I've been at this a long time, designing earth-sheltered energy efficiency. Solar photovoltaics were in their very early infancy back then. It was fun to hear that Amory Lovins was here last week. Amory and I have shared many conversations over the years. I consider him a colleague and a friend, and he is the scientist. He's the number cruncher. So Amory's quite a designer. So that's what I've been doing. I've been doing energy efficient buildings for a long time. And as the presentation said, it's crossing the Great Divide. The challenges and opportunities we have to get from here to a fossil fuel-free future. And I'll kind of walk you through some of those challenges. But these challenges aren't unsurmountable. What's really true is that, when you think about it, for the last 55,000 years, our species has been focused exclusively on food. And it wasn't until about 2,000 years ago, the Romans really perfected ways to move food and water, and they created some great architecture and also were kind of cruel along the way. But in the last 200 years, you know, we've become an industrialized nation, and we've had challenges along the way that were very different from what they are today. I think our challenges today, we can start to talk. The reason we're having a lot of these discussions is climate change. Climate change is a big subject. And you can't find two climatologists generally who will agree on what's going to happen, where we are, what's the problem. The reality is current science says that the Earth moves into a period of glaciation every 30,000 years. And if you want to read about the science of that, you can look that up online. It has a lot to do with the salinity of the ocean and how ocean currents move warm equatorial heat north and south to create the temperate zones. What's really true is that transition from glaciation to what we have now is a slow process over 5 or 10,000 years. Problem we have today is we have exacerbated that process with the amount of carbon dioxide and waste we're dumping in the atmosphere, methane, CO2, other chemicals, that we've exacerbated that at a rate that is clearly affecting the climate in terms of major storms, major disruptions of what has been average temperatures, that sort of thing. But again, you can drill down, you find that, well, you know, this is going on now, but it's also true if everyone's heard the story about Iceland and Greenland, and that Leif Erikson called Greenland green because it was a real estate scam to attract settlers on his land. Well, some of that's true, but the other thing that's true is when you look at it, when he discovered Greenland, it was in about 870, about that time period. Well, climatologists have now discovered that there was what they call the middle warming period. From that period, it lasted 300 years. And in that period of time, if you read about how that impacted cultural development, scientific advancement, knowledge in Europe, it's incredible. But what's also incredible is Greenland probably was green, that it still had glaciation in the middle, but that the shoreline, that all the fjords and bays and inlets were in fact navigable, that there was a lot of grass and things like that growing all around Greenland. Well, then what happened after that 300-year warming period, where temperatures were warmer than they are today? I think I read it was like they think now it was 1 or 2 degrees warmer than it is today. So they were able to support crops and food production and settlement, and they made it all the way to Newfoundland. After that 300-year period, and the climate sort of shifted back to normal patterns, Greenland chilled, the bays froze, food production dropped off, and of course we know the story of the way Greenland is today. So there are these climate fluctuations, but the point is climate change is certainly being exacerbated by what we're doing, and that's because of the things that we're doing to produce the energy that we need. This chart is interesting because it shows you. It gives you an idea where we are today. It shows a line at 2009, but it all goes out to 2035. And I recently looked up this source again. It really hasn't changed much. It's changed a little. You'll see it on the next chart, but you can see where the renewables fall, where coal falls, natural gas, oil, and other liquids, and nuclear. So it's a pretty startling picture when you see that renewables are still sort of in their infancy. Let's see. Why does this button... There it goes. So this is from 2019. I need to find some more current information. But again, you can still see that renewables are a fraction. But the good news is, look how far coal is dropping. Coal is starting to drop off. But we're still fairly dependent on petroleum and natural gas to have us a sustainable and regular use of energy. And this is where we are today. We all know this. Power plants are using petroleum, natural gas, those sort of things to create power. And as we just experienced this winter, dependable power. There's been a lot of conversation, and you hear it on the news media and around the country. Oh, Texas has so much dependency on renewables. That's what it was. It was the renewables that failed. No, our renewables, well, yes, our renewable sources in terms of wind did fail. But the reason the wind failed had nothing to do with the technology of the turbines. It had everything to do with deregulation and the fact that the producers were not required to provide winterization. That's why valves froze up on the natural gas pipeline. And that's why the turbines couldn't run. It's just like an airplane wing. The turbine blades ice up, you have to shut them down. They start to cavitate. And the next thing you know, you got turbines falling to the ground. So they had to shut them down because they were icing up. Now, I don't know if any of you have ever been to Copenhagen, but they have a line of turbines, wind turbines that go all the way out Copenhagen Harbor. And that harbor is subject to temperatures that are as extreme as what we experience, perhaps more. They don't have any problems. Well, it's because they have winterization on those turbines. It's called de-icing. And so it wasn't the technology that was the problem. It was the fact that deregulation allowed the producers to say, well, we've never had a freeze. We don't need to provide winterization. Well, we just had an event. I think it was maybe a 200-year event, but point is we had an event and things froze. So the argument is we need fossil fuels that produce smokestack effect to provide a regular and consistent source of energy. That may be true, but I see this as an engineering problem. I don't see this as a technology problem. So the effects of our current energy generation, this gives you an idea. This is CO2 emissions around the world. And you start to look at this and it's even larger now. You really get a sense of what is going on with all this CO2 we're pumping into the atmosphere. And you can see who the biggest players are. Clearly there's, the China, the United States, European Union, Russia, and India are the biggest ones. This is still a 2019 piece of data, but the renewables have popped up. You can see we're up to about 17%. I think I read a couple days ago, we're like 18.5. Nuclear is pretty much the same. Coal, again, is dropping, and natural gas, petroleum sources are still pretty significant. So the promises are renewables. Renewables can lead us to an interesting future, can lead us to a cleaner future. Oh, go back. Hang on. There we go. Now it's working. So the renewable horizon, I think, is important. When we think about, for the last 55,000 years, the human race has been primarily challenged by and focused on producing food and clean water. So in the last 200 years, we've created all this wonderful technology, the Industrial Revolution, and we've powered that with fossil fuels. Well, exponentially, our population is growing, and exponentially, our energy demands are growing, and our technology for renewables isn't moving, as fast as we'd like. But the good news is, I guess the best news is, it gets a little better every day, and we have to stay focused on that. This is a solar array that I installed on the building that I renovated, that I office out of, and we offset 67% of the energy that we need for this building. Now that's 67% of a building that I reduced its energy demand for heating and cooling by 47%. So it's providing 67% of that 47% reduction. Now, could have been much higher, but we left some areas on the roof. The owner at some point in the next few years wants to create a rooftop area so that people can go up and enjoy the sunshine and get out of the building. The mechanical units, I'll talk more about those. It's a very efficient system. It's a VRF system, and you can see the skylights we've introduced. So I'll talk about that a bit more later. So wind, as I shared with you before, wind is tremendous. Hydroelectric energy is great. Each one of these, we have challenges. With hydroelectric, we're disrupting migration patterns of aquatic life. We're causing some downstream problems. Again, we're learning as a species, we're learning how to generate power using hydroelectricity in a way that's not as damaging. And this is how we do it. It's turbines. And so the bottom line of our energy production, mostly to a large degree, is we've been doing this as humans for 55,000 years. We're burning something. We're burning something to create steam to turn a turbine. The turbine then creates the electricity as it spins and creates the electromagnetic field and so on. So to a large degree, our energy is generated with just this simple technology. Make a turbine spin. You can use hydroelectricity, you can use hydropower, water power, and you can turn the turbines, or you can create steam and by burning something and create power, or you can create direct current by using solar energy. So those are the things that are interesting. I read an interesting little note the other day that Frank Lloyd Wright, he was an adopter of technology. burned 3 houses down because he didn't understand electricity. But the neat thing about Wright was he actually had one of the first electric generators powered by water. He had a fairly large mill creek that ran next to his home, a creek. He built a mill pond, and he had installed an electric generator, one of the first in Wisconsin. And he'd love to go out and putter with that generator to keep the electricity going. So I thought that was a pretty fascinating thing about Wright. Solar towers, I think everybody has kind of read them. It's a modification. It's not like, they don't function like a solar panel that generate electricity. These are giant mirror arrays that focus sunlight onto a tower and create super heat. On the upper left photograph, you can see the tower illuminated. And what they do is they vaporize water, turn it into steam. And at the bottom right, you can see the plant where what are they doing? Turning a generator, using the steam to turn a generator. You know, this is a 500,000 megawatt hours of electricity per year tower, which is stunning when you think about that. And when you think about the fact that take the Sahara Desert, 9 million square kilometers of sand and what people call useless land that has some of the most intense continuous sunlight on the planet. And if you could capture, using this technology, you could capture all that. Hey, wow, that's pretty impressive. You can generate electricity. But again, let's talk about what does that do to the wildlife? The desert's not dead. There's a lot of life in the desert. There's a lot of biomass in the desert. So that's another consequence of thinking along those lines. Nuclear is certainly an option. It's clean. There's, of course, debate about that. I heard a presentation from one of from a 4-star general who's very involved with the nuclear energy commission. And he was telling me about some exciting developments, new reactors that have been designed that virtually can use the waste fuel that's already been stored, incredibly safe, very little fuel, and they can create energy. But the public consciousness is so against it. These are just models on a drawing board, and the funding and regulation hurdles are significant. So we're hearing a lot about this today. You know, we're getting into the future of transportation, which is EVs. EVs are everywhere. It's you listen to Ford, GM. I mean, this is a revolution to move away from gasoline for our personal mobility on a scale that's just phenomenal, almost as phenomenal as smartphones. But again, when I talked about that exponential demand, energy demand that's growing every day, all this EV is great, but how are we going to provide the power? We still have to plug this thing in. You talk to people and you say they're getting an electric car, and I'll share with them, hey, that's great. I think EVs are great. I have one. I said, but do you ever think about where you get the power for these charging stations? Oh, well, you just plug your car into it. I said, but how do we get the power to these charging stations? And they don't make that connection. Now, very few people make that leap and realize that EV is great in so many ways. The air will be cleaner, personal mobility be a cleaner way to move around, much more efficient way. Electric vehicles transmit energy so much more efficiently than fossil fuels, but we've got to generate that power. So it's creating this exponential demand for energy. Renewables are getting us there, but not as fast as we'd like to. So what does that do? It falls back and puts a dependency back on burning something. What would that be? Fossil fuels to create the energy to send to these charging stations to charge our EVs. So net zero carbon neutral is an achievable goal. But to get there, it has to be a holistic approach to our entire energy model, just as it has been over the last 55,000 years to approach clean water and food. It was a holistic effort. This is another chart that kind of gives you an idea of the projections. Here's 213, you can see 240, and you can see wind's taking playing a bigger role, solar's incrementally increasing, and then you can see the rest, hydropower. This is just renewables. So what the reality of all this means is that it's probably one of the most exciting times to live in. We're looking at how do we create energy in a clean way? How do we make renewables work? How does this all fit into an equation where we can address the exponentially increasing demands for energy? And it's going to require, much, much more than renewables. Energy independence, eliminating fossil fuels, reversing climate impact will require, as I said, a holistic, sustainable approach. People talk about this, and I love this shot, growing trees for the future. And it's a little tree farm that I have, and we grow some trees. Trees are great. I think we can plant lots and lots of trees. That'll help us offset climate change. And again, it's something very simple most people can do. But trees aren't the only answer. They sequester a great deal of carbon, but so do the oceans with detrimental effects. But grass, just grassland prairie, sequesters more carbon than even trees do. But it's an effective measure of, or an approach to sequester carbon. So this is a way to try to mitigate climate change. But what is it? It's not a solution. It's a Band-Aid. What it is we're trying to plant trees, lots and lots of trees, to do what? To mitigate, sequester, and store all of the carbon that we're dumping into the atmosphere by burning things. So what is the low-hanging fruit? So as an architect, what I've always done is while I introduce renewables into my projects every way that I can, everywhere that I can, to the greatest extent that I can. But what's really true is if we addressed just the built environment, industrial applications, there's a lot of bright people that work in industry. And as Emery Lovins talks about it, the interface carpet, forgotten his name now. I'm just slipping. Anyway, the founder of Interface Carpet, they both talk about waste and how waste is our real problem. Amory and I walk through buildings and he'd make this noise. He'd go, and I'm like, what are you doing? He goes, oh, I'm just standing here looking at all these incandescent par bulbs, and they're just energy vampires. They're just sucking energy faster than you can make it. And the point was, it was waste. You're turning energy not so much into light as you are heat. And so when you put a lot of heat into a building, you've got to offset that somehow. And LEDs help. They still generate heat. And so what does industry do? Over time, the light bulb industries have moved us from extremely inefficient heat generating incandescent bulbs to now LED. And there's some other kind of interesting lighting possibilities on the horizon as well. So if we address that waste equation, we can help mitigate the exponential growth of the energy demand. And so in my field as an architect, that's what I do. And I try to design buildings that you reduce the energy demand of buildings to such a minuscule amount that then it's much more affordable, much easier to introduce renewables into those buildings. And again, this is interesting because this is, if you've ever been to the Four Corners in Colorado, Arizona area, this is Mesa Verde. These people didn't have transistors. They didn't have, tubes. They didn't have the technology we have today. But one of the things they did learn about was how to collect water. And you can see that staining on the face of the cliff there. They could collect water in the reservoir in the back. They built this out of natural materials. They built it under the overhang of a cliff, creating a dynamic passive solar environment where in the wintertime, the faces of these buildings were in the sun and absorbed that heat. So when the desert cooled down at night, they were warm. In the summertime, that cliff projects out enough that it shades all of those faces. So they stay cool. So they cool down the temperature they lived in. So that's the fundamental application of passive solar. Now, just a sidebar, the archaeology at the site has discovered that it was once, when they started building this, it was pretty much a tropical rainforest. And when the people left a couple thousand years ago, it was a desert, as you see today. And what they did is they transformed that area, terraforming almost. They pretty much destroyed the natural flora and fauna to the extent that at the bottom of the pile, they found fauna, things that they were eating that were indicative of animals you'd find in rainforest. And at the top of the pile, they're finding desert wildlife. So they basically ate the environment away, and they cut all the timber to build these roof structures and so on, and to use it for cooking and that sort of thing. So they altered the environment to the point where it could no longer sustain the population. So while they were natural geniuses in terms of heating and cooling, water collection, on the other side of it, bad farming practices and harvesting practices, lumber foresting practices destroyed their civilization. So the thing that I always talk about is, where is the sun? Some of you may already know this, but passive solar design is knowing north, south, east, west, shading, natural ventilation, daylighting. All of these things can reduce the amount of energy it requires to heat and cool a home or light a home tremendously. Shading and daylighting, these are little, tools that I've got in my tool bag. Fixed shading devices, green screens, living walls, trees, knowing where to plant trees, landscapes to shade public spaces and pathways. How many of you walk across a parking lot to go to class, go to work, and you cook? You just literally cook and your shoes get hot because you're walking against a gigantic thermal mass that's collecting all that heat. Excuse me. So this is, pretty simple stuff. We all know this. Sun shines, windshield heats up, cars burning when you get back in. Sunshine is kind of diverse. Some of it's direct, some it's absorbed, some's diffused, some is scattered, some's reflected. But knowing how much, and this is where the engineer or scientist part comes in, how much you can collect and how much you can reflect and all those sort of things impact us. What's also true is that what causes our seasons, the Earth, is sitting on an axis that's inclined, and we rotate around that inclined axis. So different parts of the globe are closer to the sun at some times in the year than others. What's also true, most people don't think about it, but we don't rotate perfectly around that axis. We cavitate, which means it wobbles. So the Earth wobbles, and it's a range. It wobbles within a certain range. So our orbit around the sun is more like a spirograph, which goes back to that 30,000 year cycle. Every 30,000 years, we have glaciation, and every 100,000 years, it's a big one. So the Earth pulses back and forth because of that cavitation. But this is the simplest diagram I think you'd ever see in terms of what happens with sunshine and how it impacts our built environment. This goes to show you that, okay, so here's, if you pay attention to what the sun does, where is it in the sky? How high is it? How far does it reach to the right and left? Where's shade and shadow and those sort of things? Won't get into the whole science of this, but effectively, the sun is a constant, and that's what we use to work with our buildings to assure that we can reduce the amount of energy required, have better daylighting, and mitigate the interior environment. Again, this is probably very rudimentary, but it's true. You put a small amount of glass area in the north, and this works in the northern, and it's reversed in the southern hemisphere, of course, but it's the same thing. And you can see where you put moderate glass, and you see where you put a lot of the glass. These are the other impacts you start to think about. You think about wind. What's interesting is with our built environment, particularly in a dense urban area like Dallas, we've altered the wind patterns to where if you go north up to Denton and further north, it can be 105 degrees down here because of the heat island effect, and also the wind doesn't move through here. And if you go up north, it's a lot cooler and there's a breeze because they've mitigated two things: the heat island effect, and they're not blocking the natural wind patterns. So put that together for a building, and these are the kind of influences that we work with every day. How much heat loss, how much heat gain, how much daylighting. Pretty simple, really. And this is the simplest concept of all, shading. So if you take advantage of the sun is almost vertical in the summertime, lays down to our latitude about 32 to 34 degrees in the wintertime. You can use that to your advantage. So if you keep the direct sunlight out of your building, out of your windows, you're not gaining all that heat gain on your thermal mass. And in the winter, you let it in and warm it. Some technologies work better in climates than others. For instance, in Dallas, skylights are horrific. You just can't control the amount of heat gain that comes through skylights. I love skylights, but they're a very difficult thing to use. There are technologies that we employ that do work. But north of us, north of the Mason-Dixon line, skylights are great. And here, what works better for us are clear stories. So very simple, very, kind of basic techniques. So in climates where the sun shines, heating is easy. This is basically a sketch of a trum wall. Sun comes in, passes through the glazing, just like your car window. It hits a heavy thermal mass, and you get cool air coming in the bottom, warm air out at the top. It's called a trum wall. The other thing I want to talk about is, and we'll go back to the trum wall in a minute, but let's chat about Iceland. So when we talk about renewable energy, Iceland is on the verge of being completely energy independent with a renewable source. And what is it? It's geothermal. This is the Blue Lagoon. If you've never been there, I recommend you go. You can move around in the Blue Lagoon. There's some areas that are so hot you can't even go into, and the other areas, it's just amazing. And they have these hot pots all over Iceland, and I visited several of them. They're really fun. Well, the benefit Iceland has is sitting on three major tectonic faults, and so they've got this tremendous advantage of being able to tap into those tectonic faults where you basically have magma down there, and they have hot water geothermal vents everywhere. But it's pretty amazing to see that they generate virtually all the electricity for Reykjavik and the other major cities from these geothermal sources. So it's wonderful, and it's great that Iceland has that ability. But here in Dallas, we're not sitting on any tectonic faults, so we really can't take advantage of it. But again, what are they doing? So they're not burning anything, but the core of the earth is so hot that they produce steam a different way. They tap the geothermal vault, create steam, make the turbines turn. So this is the trum wall that I talked about. This is a sketch in the lower right that I've done. And when I was much younger, much younger, in 77, I experimented and built many examples of all of this. And effectively, here you see it again. It's as simple as thermal mass and heat collection. Works great in cold climates. Trouble is that I'd soon discovered was the best light coming into your home, and the thing that makes a home comfortable, feel good, just a pleasant place to live, is the sunlight and the daylighting that comes through the windows. When you put windows on the north, the east, or the west, that's problematic in a lot of climates, depending on what you're doing. And the bottom line here is you have to add lighting to light up the dark space. This is kind of a hybrid that I did once. I put little glass blocks in the wall, and it worked, but it's still, you're facing that heavy mass. These are some other examples where you can use tubes of water, let the sunlight hit that, warm it up, store it, and reintroduce it. The stone in the upper left was a stone wall. These are not my designs, but you can do that too, collect it on a stone wall. This is a sketch that I did, which shows kind of a hybrid. You create a trum wall where you pull the air in, how it moves. Again, great for heating, destroys your view, just unworkable. Now, Amory, I don't know if he talked about it in his presentation, but he talks about how he harvests bananas in the middle of winter at his place in Snowmass. And what he has is he has a modified trum wall. He has a greenhouse that you see on the left. He collects the heat. He uses that heat to condition most of his lab up there. And he can grow bananas in his greenhouse. And again, that's an extreme northern climate, works great. Well, we've got the exact opposite problem in Dallas. We have the issue of cooling. We get too much heat. This is something that's pretty interesting, and it's a trum wall, just a modified, more creative way to think about it. You create a thermal mass behind the glazing and use it that way. Now, kind of some things that we played with, not to great success yet, is can we collect that heat and extract it out of that wall and actually do what's called it's a conductive cooling mechanism. You put it in a masonry wall, something like that, absorb the heat, or you pump coolant through it to cool it to take the heat out. Again, this is almost going back to those early days when we were doing the solar panels, pumping water through them on roofs, and you had to be a master plumber to condition it. So I think there's opportunity here. We're working on it with different refrigerants and seeing if there's a way that we can actually create a link to make walls, floors conductive to extract the heat out of the air. So when we talk about buildings, and I won't get into too much of this, this is more about the way that we approach a building, whether it's a small home or it's a large facility. And where we start is baseline modeling. And we really look at, that building, how much load, what do we need to do to offset that load? I mean, you've got to deal with cooling, you've got to deal with lighting, you've got to deal with plug load. Additionally, you have to deal with people load. One of the biggest demands in buildings that you have to offset by generating electricity, again, it's either more solar panels or more energy of some kind, is us. We're little, remember that movie, what was it, The Matrix? We're copper top batteries. We're generating heat all the time, heat and moisture. And so when you design a building, several things impact it. You have to take it into account the amount of heat that's introduced in the building by humans. We're a chemical engine. We're burning food all the time. So we're doing the same thing as we do to generate electricity. We're burning this fuel inside of ourselves, creating heat. And then we off gas, carbon dioxide. All of those sorts of things affect the indoor environment, along with heat gain, as I said, heat gain and the need for lighting and the plug loads to run all our great technology, like our computers and smartphones and so on. So one of the things that we've done recently in buildings is the building codes are catching up pretty quickly, but you had to provide 16, I think it's 16 or 17. Again, I'm not an engineer. I hire my engineers to do the numbers for me. I think it's 17 cubic feet per minute of fresh air has to be introduced into a building. So how have we done that in the past? Well, we figured out, okay, so maximum capacity in this conference room it's an auditorium, it's 700 people. How many are listening today when you sat in a conference room or a big auditorium and there's half a dozen of you in that room and everybody's freezing? And the reason it is the systems were designed to provide the amount of fresh air exchange for the full capacity of the building. No way to modulate that, no way to change that. And so one of the things that's happened, and I'll talk more about that a little further, is we've had tremendous advancement in our mechanical systems, our mechanical equipment, and our control systems, to where we can actually monitor the amount of CO2 that's in the room. So if there's only 3 people, they're not going to generate as much heat or carbon dioxide as 300 people. And there's a direct inverse calculation between carbon dioxide and the amount of heat generated by the humans in that building. So if you just monitor the carbon dioxide, create controls to adjust that, you can reduce that fresh air. Because what's going on is that air conditioning unit on the roof is cranking out. It's taking 105 degree air or 100 degree air at 60, 80, 90% humidity, conditioning it down to about 35% humidity and in the comfort zone, the climatic zone that's comfortable to humans, and then dumping that into the space. And that's just the fresh air. That doesn't include the other needs for heating or offsetting lighting loads and that sort of thing. So that is one of the biggest loads on any building is fresh air. So if you can modulate that with controls and or smarter systems, what have you done? Well, you've reduced the energy demand of that building. Now you don't have these units sucking in all that energy to create all this excess cooling to dump fresh air into a building where it isn't needed. So it's about getting smarter. Insulation. You know, we still don't properly insulate our buildings. We've come a long way. There's a lot more technology. There's some great new products on the market. I have been wrapping my buildings with a full 1 to 1.5 inch rigid insulation on the outside of the sheathing to create a completely sealed envelope, because you still get conductivity that moves through the framing and the walls. You'll find even today, I mean, I run into old buildings that the city's own or private clients, and I'll go up on the roof to see how much insulation they have. None. They've got what's called a recovery board. It's like a 3/8 inch to a 1/2 inch board laying on top of the steel deck, and then generally a dark roof sitting on top of that. One of the things that we've been doing for a lot of our clients is when they have a need to re-roof, we pull the roof off, we put R42 minimum on the roof, and then we use like a white TPO membrane. That alone reduces the demand, the energy demand, by tremendous amounts. 70% of the heat gain that goes into a building comes from the sun. So you can start to see that when you talk about things like reflective roofs, cool roofs, living roofs, insulation, all those things can reduce the amount of energy a building needs. So if you do that for one building and you reduce its energy demand by, say, 75%, you can, on residential projects, we have pretty good luck reducing it down to almost 90% compared to a standard builder tract home. So then when you look at the amount of solar PV you have to put on that roof, it doesn't take much to heat, cool, and power a building that's that efficient. Whereas the other building that's not efficient, well, you can imagine you're paying for a lot more panels, you're trying to generate a lot more electricity, you're consuming a lot more electricity. So this is the roof design I was talking about. This was an old warehouse abandoned for 25 years. We renovated. I cut these big holes in the concrete roof. We introduced these skylights, they're 4-layer skylights. They're incredibly efficient. They bring in light. You don't get any view, you just get light. And so we integrated those along with the solar panels. We put an R46 roof on this, sitting on top of the concrete deck, then used a highly reflective membrane. And that's one of the reasons we were able to realize a lot of the energy efficiency that we realized in that building. Here's another aspect, something that I think is pretty important and pretty easy to do really, and that's living roofs. If they're done well, the darn things don't leak. It just, it goes back to detailing. It goes back to craftsmanship, all those sorts of things. But the nice thing about a living roof, and you can see here, it does a number of things. One, you're putting a living material on the roof. Plants have this incredible ability, as we all know, to absorb that sunlight and reduce that long wave radiation that gets into a building. So you've got an earthen material with plants on it, you get evapotranspiration going, and it reduces the heat gain even more so than a reflective surface. The nice thing about it too is that you're not re-radiating that heat back in the atmosphere. The plants are actually absorbing it and then releasing it at night. The other nice thing about living roofs that I talk about is when you think about if you were a bird or a butterfly flying over the city of Dallas or any major city, you look down and all you see are these hot roofs with mechanical systems where there once was this living mantle of the earth. So every time that we carve out a piece of the living mantle of the earth and we put some hard surface up there, what we're doing is we're exacerbating the heat island effect. We're creating another surface that all it's going to do is store that heat. Again, it's a trum wall in the atmosphere. We're storing that heat. Well, where does that heat go? It only has two ways to go. It needs to go up or down. I get a lot of conversations. People love Adobe structures. And I think Adobe structures are great. But the problem with Adobe structures here in Dallas are they heat up during the day and that heat has to go somewhere. So in Taos, New Mexico, where the high might be 73, lots of sunshine, the Adobe warms up. And at night when it's 42 degrees in the desert, wow, it's nice inside those Adobes. It is so comfortable and that heat's coming from everywhere. So it's a very comfortable way to heat. Here in Dallas, you heat that Adobe up to 102 degrees. Well, where does that heat go at night? You're living in an easy bake oven because it doesn't cool down much at night. And when it doesn't cool down much at night, the heat's going to go both ways. It's going to go out in the atmosphere, but it's also going to come into the interior. Innovative things like this. This is just a little bus shelter and you put a living roof on it. This is, if you've ever been to San Francisco I think it's Golden Gate Park. Again, another living roof, skylights, and you can see the shading effect all around this building. Very efficient building. So these are some of the specifications that we use. And I think over time, as technology improves and we get better glass performance, the U value and things like that will increase. We generally use thermally broken frames, which means there's no conductivity from the inside to the outside because there's a thermal break in the middle. And when you look at when you look at a window frame, for instance, you would be shocked by how much heat goes out of your building in the wintertime through those frames and how much heat comes into your building in the summertime through that effect called conductivity. This is very simple and this is recorded so you'll be able to grab this. This is a chart that we perfected over doing this for 30 years plus on how to control sunlight to get the maximum heat gain in the wintertime, maximum amount of indirect daylighting, and also maximize your heat gain in the wintertime. My home in Dallas, for instance, just to give you an idea, I'll talk about this building shortly. When we had the big freeze here this winter, everybody in our neighborhood left. Power was off. People they couldn't keep their houses warm or it was just unbearable. Well, my house is a passive solar home built with insulated concrete forms. I have a crawl space that's underneath the home that I use as a plenum space to heat and cool. I have masonry floors. I have tile. So what happened when the sun was shining, sun was coming through the windows as designed, heating up the floor tile. The floor tile was a thermal mass that was saving it and then re-emitting it back into the home. We stayed fine. It wasn't 72 degrees. We never got much lower than 64 in this house, just using the sun. And so, you know what, put a sweater on. One of the things that used to drive me nuts was Pat Summerall used to advertise for Train on all the football games. And he'd say, Train, it's 72 degrees everywhere. That's dumb. You know, it's like, come on, it's summertime in Dallas. Wear a short sleeve shirt and shorts, you know, or it's 10 degrees in Minneapolis. Throw on an Icelandic wool sweater. Amazing how comfortable it can be. Speaking of that, when I was in Iceland, I picked up one of those Icelandic wool sweaters from the Icelandic sheep, which exists nowhere but in Iceland. And we went out to Thingvellir, which is where they used to have their government meetings. Cold day, 52 degrees, I think. There was no sun shining. It was kind of wet, damp, kind of misty. And so I put on that Icelandic wool sweater. I was toasty. It was so nice. I just walked around with a little, just a little rain shield and rain parka and that Icelandic sweater, and it was pretty amazing. So we can learn how to adapt to our environments. This is the Plano Environmental Learning Center, one of the first buildings I was able to do. This is a LEED Platinum, the first LEED Platinum certified building in North Texas. We integrated everything in this building. It has ICF walls. It has R42 roofs. It's passive solar design. You can see the glass here on the south. I did displacement ventilation, which is a fancy word for saying you don't blow, and in your offices that you work in, the air blows out of one vent onto the ceiling, and 6 feet away, the air gets sucked up into the ceiling. So it, again, waste. Amory talks about straight pipes and thinking differently about how you do things. In this building, in the summertime, the cool air drops from the ceiling. It's drawn down under the floor through ducts. And so the entire air volume moves. There's no blowing. You don't feel any blowing. It's very comfortable. It reverses in the winter. The hot air comes out of the floor, rises, is captured, and then is taken back to the units. So this is displacement ventilation. My home works the same way. I can change my ducts winter to summer. We've run those numbers, and it has actually increased the efficiency of the home by about 7% just by switching that. So hot air rises naturally, so it's in the crawl space. The floor is warm in the winter, the heat rises, it's pulled off the top, goes back to the return air unit, and then is reheated and sent down. So you're actually recycling that air. In the summertime, it's just the opposite. The cold air is introduced high because it has greater density. It falls, gets drawn through the crawl space, and then goes back up to the unit. So it's a very efficient way to do something without a lot of ductwork. We did put a wind turbine on this building, and it also has a tremendous amount of solar. It is probably the closest I've ever gotten to net zero with a building. And when this building is not occupied and the air conditioning set points are down, it provides excess energy to the warehouse, the city of the Plano warehouse next door. This is the interior, completely daylit. This thing, this shot I had to play with the filter because it was so much light. It was hard to really photograph. But you can see here again on the left, those are diffusers that the low sun angle in the morning, when they have a lot of conferences and classes in here, we had to mitigate that. So I designed this diffuser that the light catches the light, blocks the glare, and throws the light up on the ceiling. And then the rest of the glass fully illuminates the building. This is a building up on the University of Texas in Denton, and they used very similar principles. We had written some guidelines for this project when they were designing it. And so the little glass diffusers really are more about design than they are solar heat gain. But you can see the overhangs. This is another building where they started to pay attention to thermal mass, glazing, south-facing windows. And again, these last two buildings were LEED certified, both of them gold, I believe. And again, you can see you can use these principles to design buildings that take advantage of both the thermal mass and the daylight coming into the buildings. This is one we just finished in the city of Plano, and we had this is a 2-story lobby in here, and it was south facing. They wanted a daylit, so I created this shading device, which really lets through only lighting, and you can see the diffuse pattern. And what's fun about this is it's beautiful at night too. The light that comes through the back, you can really see the patterns through the perforated metal. So that has worked very well here as well. We get the daylight and we don't get the intense solar gain into those spaces. This is the interior of that UNT project, and the entire space is daylit. And they introduce skylights. This is a wonderful way to think about buildings without having to provide a lot of lighting. I mean, it's wonderful, and it's part of the student union. The kids and students just love this space. This is a bridge walkway that goes across. It could have just been a hallway that had artificial lighting, but instead they did it with glazing. Fortunately, it's east-west. The west side's a little problem, but you can see all the trees there on the left, and that's the west side. in the building I showed you, the 1808 building, this is what we did with the skylights. So there was no natural daylighting in this building. There wasn't even a window. We cut it all in. On the left here, this was the old boiler room. And when we renovated the building, we decided not to put a roof over that. And we used what's called cowl wall, which is another kind of skylight system that provides natural daylighting without all the detrimental effects of excessive heat gain. So windows can be used to a great advantage. This is a south-facing window in that same building. That warehouse we renovated, and it has an overhang. You can't really see it, but this is in the middle of the day, full sunshine, south side, and you get this wonderful diffused light. What we're doing a lot now is we're playing with this quite a bit. This is one of my buildings, but we're playing with living walls, living screens, and they work the same way. And you can do this at your home, you can do this at your office. So what you do is you've got a Western exposure or a Southern exposure, you can create a living wall with deciduous plants. So in the summertime, it absorbs the heat, knocks down that direct sunlight that creates the heat, creates the problem, but it also creates a conductive cooling environment because the plants have evapotranspiration where they off-gas moisture. What they do is they create this sort of maglyph effect, which is something that was perfected by a Saudi architect generation ago. And he discovered that he could create these towers and move air through them. And in a way, he would create this condensation, and so the hot air would come, move through, pull the air out of the buildings, cool them down. Well, we're finding we can do that same thing with these plants. This is nothing more than cables and a climbing vine. Another aspect of this, which is really fun and bringing in that sort of biophilic or natural approach to building design, is that in the wintertime, since these are deciduous, they drop the leaves and you get the solar heat gain to heat the building. Again, what you're doing is you're reducing the amount of energy to heat and cool the building, which there again reduces the amount of fossil fuels that have to be burned to generate electricity, which then also reduces the amount of solar panels you need on your building. Living walls. There's a big skylight over this. This is an amazing thing to see. That's all of that plant life there you see is living and really mitigates the interior environment. Lighting. Lighting is a big deal. 15% of the building is artificial lighting. And of course, when the sun sets or shines, you've got to provide artificial lighting of some kind and in some way. But you can also prioritize it. And you can see on the lower part of this slide, you can see where you start to think about common areas, parking lots, classrooms, offices, storage and mechanical rooms. You prioritize them in terms of the amount of natural daylighting you use. You prioritize them in terms of the light levels that you use and so on. One of the other big things in lighting is circadian lighting. I don't know if many of you have listened or heard about that, but what's true is our bodies having evolved with the sun, night and day cycle, that sort of thing. It's called a circadian pattern. And the light in the morning is a different temperature than the light in the evening. So we have evolved to where the wavelength of the light in the morning makes us alert, brings us to that alert condition, all this weird stuff that our body does that we don't know about, right? And in the evening, the temperature changes again and puts us into more of a sleep state, moves us more to a natural sleep state. Well, you can play with that spectrum with lighting to the extent that a lot of sports teams now in their locker rooms are using the wavelength that gets the body stimulated because they're playing games late at night where the natural tendency would be to shut down. They can change the circadian pattern of the lighting and change the wavelength so they're exposed to more of a stimulating light than they are one that would tend to move you to sleep. So that science is still in its infancy. That technology is still in its infancy. But this is a building we did this building. It was another LEED building, LEED Gold, City of Dallas. All of the classrooms are naturally daylit. The lights are on only for the photograph. This classroom is completely illuminated with daylight. That's a light shelf that you see, and the light comes in, and they use these classrooms without even turning the lights on. The lights that are in here are photosensitive. They have controls. Again, when I told you about smarter controls, the controls actually monitor the level of light in the room and adjust the amount of lighting you need to keep that balance that's perfect for whatever the task may be. And you can set the task up if it's reading or if it's learning or whatever it might be. And what's nice about this is, again, the controls have allowed us to move from just turning on a switch. And when I was first got out of school in 77, you know, we would have to design, and the engineers I was working with at that time thought I was nuts. I'd have 12 switches in a room. And of course, then, you know, you'd have to get into value engineering and I'd only get 4. But the point was, I was working to modulate the amount of light. So as it got darker in the room, you could flip more lights on so you get a light level. And I was doing this in 77 where nobody even understood what I was trying to do, which was reduce energy demand. Well, now we can do it with good controls. This is the Plano building we just finished. All of those, again, daylighting. This is a retail space. Those lights are merely there to provide light when it's dark. But this is a retail space. And now this building is finished. I need to go back and get photographs, but the retail space is lit very well. This is also a really efficient building. We did a lot of shading, did a lot of insulation on this building. We could not do any PV. There wasn't any budget for it. We used some very sophisticated controls, very sophisticated equipment. And we got this building down to about 47% less energy consumption than a comparable building. Equipment, I'm not going to dwell on this because everybody's eyes kind of roll when you start to talk about it. But for me, one of the most exciting things is our HVAC systems. And to me, it's fascinating when you go into old buildings and you realize how old these mechanical systems are. And they're consuming energy, just an incredible amount of energy to run. They're very inefficient. The controls are terrible. And so you've got buildings that are, again, Amory's great sucking sound, and you're just burning energy that has no purpose. It's just wasted. It's just gone. So as I said, for me, what's exciting is we're starting to look at things where we can reduce the energy demand on buildings just by having more and more and more efficient equipment, which is, again, go back to that, for 50,000 years, we've been trying to solve the food equation. Well, now we're working on efficiency equations, and we're working on ways to create much more efficient buildings. So to me, it's exciting. A lot of people probably yawn. But the other thing that's really true about this is that CFM equation, which has always been the kicker. You can design a really efficient building and you still get kicked in the stomach because you've got to provide 17 cubic feet per minute of conditioned air for every person in that building. Even though we have better controls to modulate that, it's still a tremendous amount of fresh air that you have to heat and cool. Well, we're looking at things now that are really fascinating. Upgrading the filtration. And here's another exciting thing. COVID has thrown this into, you know, what's that ludicrous speed? It really has, because now we're looking at HEPA filters, ultraviolet treatment, bipolar ionization, and there's some other new technologies. So distill this down. What does that mean? We used to provide well, we still do, but codes require it. But instead of providing 17 cubic feet per minute, why do we think about buildings as if they were the space shuttle or a space capsule? They can't lose any air. They can't add any air. They have to filter the air when the astronauts are in there. And if you ever watched Apollo 13 and what happened when they didn't have the filtration on. So there are systems now where we can actually charge a building with fresh air and then produce an indoor environment where the air is better than it is outside by cleaning it and just simply reusing that air over and over and over. If we can get this to the level where it'll really work, but it requires a commensurate improvement in ceiling buildings, that sort of thing. Pretty good at that, but still, buildings still leak quite a bit. But the point of that is, once you charge a building with air, you don't have to provide 16 or 17 cubic feet per minute for every person in that building. You take that load off of a building, now you're so close to providing net zero in terms of energy that the technology we have in solar panels would do it. And it'd be very easy to do, even in high-rise buildings. So this is, to me, this is pretty exciting. If we can crack that nut, that's going to go a long way to getting us to net zero with buildings, which then ultimately reduces the energy demand and so on. Because still what's true is panels today are still only about 24% efficient. Somebody can correct me out. Someone told me the other day that they thought we were up to 27 or 30% efficient with solar panels. I haven't seen that data. I'd love to see that. We're a power plant, a fossil fuel power plant is about 33% efficient. And the trouble with that is you're still dealing with entropy where you're losing, you know, it's storage and transmission. You're losing energy when you send electricity through wires because the longer that has to go, it drops off. It's called entropy, where the energy It converts from electrical energy to heat energy. So transportation is always an issue, and storage is storing it's another issue altogether. But we've come a long way. This is a lot of industrialization was based just on water power, and I think that's pretty exciting. But from this to this, where you're starting to see these are the University of North Texas new facilities that we've been working with, and you can see the controls. You can see the big straight piping, not a lot of on the water side and the steam side, not a lot of bends. And it's almost art in some ways. This is an incredibly efficient cooling tower, much more efficient than any cooling tower ever built. Recycles the water, which they've been doing for a long time, but it's how the water is introduced and so on. This is a thermal storage tank, which is an experiment that they're doing where they're trying to store some thermal energy, where they're actually chilling at night, chilling water down at night and storing it in these tanks, which are highly insulated. And that's been done for a while. Minneapolis, the University of Minnesota, I think in the early 70s, built buildings where they had these big, kind of like during Jefferson's time, they had these ice vaults. In Jefferson's time, they used to have, they built an underground building with timber, like an underground tank of timber. It was called an ice house. And what they would do is they would cut ice from the river all winter long and store it in that ice house. And then they'd bring the chunks of that ice into the house in different ways to cool it. Pretty ingenious. He was a pretty smart guy. And he came up with some ways to bring that ice in and actually provide some cooling, but also as far as mint juleps and whatever else. But it's the same concept. University of Minnesota did the same thing. They chilled, in the wintertime, they filled this, they froze this vault of water, and then they used it for heating in the summer. And to this day, it's still a pretty effective system. These are some new systems, variable refrigerant flow. They talk to each other. They move heat from one side of the building to the other. So the energy that they consume is very, very little. They monitor the wet and dry bulb temperatures. You can dial these down to where they're just dealing with humidity and not providing any cooling. So these are pretty amazing. They're all interlocked. Weatherization. I mean, this is the biggest, one of the biggest things. If we just did things like weather stripping on doors and windows, upgrade or replace door sweeps, replace open or aging sealants, unsealed openings, mechanical penetration, gaps, pathways, cracks. The amount of exfiltration, infiltration to our buildings today is just phenomenal. That alone saves a tremendous amount of energy. And again, it's that great sucking sound. We're not using energy for no purpose. Software, this talks a little bit about the controls. And again, I'm just going to gloss over this. But one of the great things and exciting things for me is that we now have controls, a better and more sophisticated controls, thanks to microchips, where we can control everything: CO2 management, economizer cycles, optimize sequence of operations, all those sorts of things. Maintenance sounds silly, but just cleaning your coils, changing your filters makes a huge impact. Checking your refrigerant loads, looking for leaks. I did a project in Laredo, Texas. It was a big project. The building got fired up, and I got a call from the building manager at the end of summer, and they were having problems cooling the building down. So I flew down there, went up on the roof, and I took the panel off. I had the mechanical guys there, but we took the panel off the air conditioner, and we tried to get the filter out, and we couldn't. The filter was an adobe brick. And so the cooling coils, the condensating coils, there's a lot of dust in Laredo. And so you've got wet copper coils that are trying to condense the heat and just expel the heat to the atmosphere. So they're sweating, dust is blowing on them, and they actually created adobe bricks. We could not even get in there. They had to dismantle the units, and the filters came out as bricks. And then the coils were shot. And so I asked the maintenance man, I said, well, when was the last time that you followed the maintenance schedule to come up here and pressure wash these coils every 2 weeks? I've never pressure washed them. Well, there we are, so that's part of the problem. So maintenance is a big deal. Going back to controls, this is an interesting shot. For me, it's aesthetic. It's beautiful. These are called pneumatic controls. The piping is so precise. It's straight. All the angles, look at that. All the angles are the same. It's just amazing. But these are the old controls. These were in the 70s. These were the cat's meow. These things, this is how you controlled zones. This is how you controlled valves, and all replaced now by microchips. But I find them interesting in that, you know, this is a technology that's gone, but you still find it. You find this in public buildings and major buildings everywhere. And when you look at it from today's perspective, these things are incredibly inefficient. They're just inefficient, but they're a beautiful work of art. I mean, I can't get a plumber to lay a level pipe for a waterless urinal, and yet look at the craftsmanship that went into this. Again, more of these controls. This is sophistication that we're looking at today. And this is what's helping us really reduce the amount of energy we're consuming. This talks a little bit about light harvesting sensors, occupancy schedules that match calendar and program use. These are all little things that you can do, but they save energy, and they save energy incrementally. I talk a little bit about biophilic design, diurnal lighting patterns. And so occupant behavior plays into this whole concept of reducing energy consumption in a building. When you look at what I've just shown you holistically, you can see that you can reduce the energy demand of buildings down to something very small. And hopefully in some ways, maybe it can offset the exponential growth in power generation we're going to need for EVs. So they kind of work together, and they work synchronous in a very synchronous way to create the kind of efficiencies we're looking for. But when you think about occupant behavior, and as I say here in the slide, you can make a tremendous benefit. You know, mobility integration, you know, just people will bike ride if there's a place to keep the bikes and where you can put them. This is in Copenhagen. And I was just amazed by this. When you're in Copenhagen, there are more bikes than there are cars. They're everywhere. And you see Vikings, you know, cruising around all through the city. It's fantastic. And then wellness integration. That's the other aspect of this, which is thinking about how we design buildings so that people can get out of the space, go outside. It's a healthier environment to work in. If it's a healthier environment to work in, they're going to be more aware of a number of things that affect the way they feel in the space and how they use the space. And surprisingly, it does have a contribution to energy reduction. So it all comes down to this: integrated design, where you start to think about designing buildings and energy systems that support those buildings in a holistic way. And this is the way that we're going to move. We're going to move through this middle ground from where we are to where we want to be in terms of net zero and a 100% renewable energy generation. And it truly is science, engineering, design, architecture, holistic thinking. And it's those kind of things. It's just little things. When a goofy example, when you walk across a parking lot and you see a crushed Coca-Cola can or whatever, you know, the Red Bull can, whatever. If you recycle that can, and I've been saying this for a long, long time, you recycle that can, it's the equivalent of operating a big screen TV for 6 hours. That's how much energy you save just by recycling that can. So next time you go to a gas station, you look down in that trash bin and it's full of, you know, crushed aluminum and bottles and all that sort of thing. There's where you can also make an impact. And it goes back to this holistic thing about energy consumption. If that recycling that one aluminum can, rather than sending it to a landfill, can provide 6 hours, the energy saved provides 6 hours of operation on a big screen TV, add that up. It doesn't take long. You know, if it's one person, you know, Dallas is what now, 3.4 million people. How many cans of aluminum get thrown away versus those that can be recycled? So my point is, renewables and getting to net zero just isn't about more efficient, bigger, more solar, more wind, more of those things. It is, but it's also very integrated with the concept of let's reduce the demand. Let's get rid of waste. So by reducing demand and eliminating waste, it doesn't take as much renewable energy to do the same job. And that's pretty much what I want to share with you this morning. So Rosa, how we can take questions, of course, and just let me know how you'd like to do that.
Hi, Gary. I thought we could go back to the beginning. There aren't as many questions as I thought there might be, but I think there are a number of questions that were submitted by the participants, by the audience.
Cool.
Let me start out with, and I think you addressed this one. I think Melon. Get down there. I'm not down there
Melon asked a question regarding reflective roofs and white
Yes.
roofs and the efficiency. You actually presented that as part of your the reconditioning or the remodeling you did at Good Work. But you want to talk about that a little bit more about how much additional efficiency is gained by going with cool white roofs? There's been a lot of discussion on that in the community.
Yes, it does. There is a benefit to using a white roof by reflecting the energy. It needs to be coupled with increased insulation to truly be effective. But a white roof alone, just the white roof, can reduce the energy demand. Well, as I said, you take, for example, A&M did this study a long, long time ago, and in the 60s, I believe, and that's where they determined that 70% of the heat gain that comes into buildings, this was in Texas, is from the roof. And providing a thermal siphon roof or a reflective roof that has high emissivity, you can reduce that heat gain close to like 75%. That much can be offset just with that reflective roof surface. So then you just insulate against the differential, and that's what makes the real difference. Now, that was it. I set a timer. Because I get into the talk and then I forget about looking at the time. But here again, one of the last slides I talked about was maintenance. I have seen so many, and 1808 is a good example. I've been bugging the owner now for 2 years to get someone up there to wash that roof. And of course, it's one of those things, well, it's not a maintenance issue. Well, it's not. It is. The roof's fine. It's not leaking. That's not the point. The point is a white roof is great when it's white, but over time, with moisture, condensation, mildew, algae, all those sorts of things, the reflectivity, you begin to lose it. Now, a metal roof that has high emissivity that stays fairly clean is a much better roof in terms of maintaining long-term efficiencies in terms of re-radiation and reflection. But white roofs are great, and they're great for about the first 5 years. And after that, when you look at the numbers, they begin as the reflectivity diminishes by the amount of dirt on the surface. So you go from a white roof to a brown roof to a gray roof to almost a black roof when the mildew is there. So what have you done? You haven't done anything unless you maintain the roof. So white roofs are great. That's where you should start. But the reality is, over a period of about 10, 12 years, they fall back to just what a standard, dark gray or black roof, not quite a black roof, but they fall down. There's still some resultant benefit from the fact that it is still a white membrane under that dirt. So that's a problem, and you have to maintain it. Now there's some really interesting work being done with titanium oxides, and the titanium oxides, what they do is that material actually, the sunshine reacts with the titanium oxide in the surface, and it kills everything. I mean, it kills all the mildew, it kills all the things that create the dirt. It kills, and then a rain, and it washes itself cleaning, and it washes itself off. So if we can, hopefully if people are a lot smarter than me, can figure out how to get titanium dioxide as a surface coating on white roofs, that's going to perform a lot better. So yeah, they're great, but just realize you got to keep them clean.
Hey, Gary, is titanium oxide environmentally friendly when it washes off with the rain and goes into, your landscaping and things like that?
I had that same question. What I read was it doesn't wash off. The reaction occurs on the surface of it. So it isn't like a titanium dioxide has a reaction with the dirt, and then whatever that layer of the titanium dioxide washes off, it's more of reaction with the dirt. And I don't know if this is true, but somebody told me that you don't see it on the label, but titanium dioxide is in toothpaste and has been for a long, long time.
It either creates cavities or prevents them.
Yeah, I'd like to know that.
One of the first questions we got was from Skip Cave, asking what your recommendation is for the 3 to 4 most effective energy saving things you can do when designing a new commercial or government building. 3
most energy efficient things would be, number one would be the envelope. making sure the envelope is highly insulated. Number 2 would be the roof. As I said, we need to think about a very, very efficient roof. 3 would be the mechanical systems. It's hard to, there actually has to be the fourth, I guess the first one is orientation. How you orient the building to take advantage of the passive solar influence so that you don't put a lot of glass on the west because the building is just going to overheat. If you put glass on the south, it needs to be shaded. Even the, you know, there was a study done, again, this was back in the 70s. I could probably find it somewhere in my notes. The city of Austin, it was UT. UT did a study in the city of Austin, and they tested glazing systems. And what they found was that the most efficient glazing system on the market, three pane, argon filled, high shading coefficient glass, did not perform anywhere near as well as single pane glazing that was properly shaded. And I thought that was amazing because you would think you'd get more conductivity through the window in the winter, which you do, or conductivity through it. But the conductivity aspect of it was offset by when you shaded that single pane window and you had no direct solar heat gain, it offset that. And so just a simple single glaze window with shading way outperforms the most efficient, highly reflective, low E, triple pane, argon filled glass that you can buy. So that's where, you know, again, it goes back to this integrated design. What are the 3 big things? Orientation, and with orientation, there are then bullet points below that, which is what way is your glass face? What's the U value of the glass? What's the reflective aspect of the glass? Is it shaded? You know, so there's subcategories. So I would say orientation first, building envelope, the integrity of the envelope, highly insulated, sealed very well, and then perhaps you could throw the roof as a subcategory under that. Just a well-designed roof system, which would go with the envelope. Just a well-designed envelope, highly insulated roof, walls, glazing, so on. And then third would be those mechanical systems to take advantage of the new equipment that's out there so that you can mitigate that fresh air. And I think now, again, underneath that mechanical system, the new one would be, we need to think about fresh air, because one of the things they found with COVID is that 16 CFM did not stop COVID. They found that what it had to be was the rates for fresh air had to go up to almost, I think it was something crazy, like in the 70 cubic feet per minute. So then what have you done now? So now if you're introducing 70 cubic feet per minute, look at the exponential growth of the size of the mechanical systems and the energy demand to provide that. So, whoa, that's a step backward. Now we're trying to, you know, we're trying to, you know, pound a nail with a sledgehammer. It doesn't make any sense. So some of the more sophisticated filtration systems as part of that mechanical system, I think, are also can significantly help us reduce energy demand in new buildings. And
hey, Gary, Michael here. You know, in regards to those mechanicals or the air filtration, is that, and it deals with water filtration as well, is that the filters. I mean, you have to replace them, you know, for them to be effective. And then the problem we've had is the recycling of those filters. And then you know, so how, do you have any answers to that, and what kind of research is going on?
Well, I'm involved with a company, and I can't share what the company is, and I've got disclosure requirements. It's using technology kind of like the titanium dioxide type filtration and infrared light and a number of other things, where the filtration is really only going to capture, it'll only need to capture solids. And that filtration can be cleaned and reused. So it's an interesting technology, but yes, you're right. I mean, when you have, I mean, I've got, in my house, I've got the April Air, the MERV 13s, and I get about 6 months of use out of those. Generally, well, the house is pretty tight, so my filters don't get dirty very often. Sometimes I can go a year. But at the end of the day, you know, I've got this fibrous filter that's 6 inches thick, pleated. I can't do anything with it. You know, but it is, you know, it is a fiber. It is a cellulose-based material, so it could be composted. That's one thing you can do with it. But yeah, that's the problem. The filter is a throwaway. So now what are we doing? So here again, we're back to the waste equation. Stuff's going to a landfill.
Could be a biofuel if there was.
Yeah, biofuel. But you see how this is where it takes that holistic thinking, because you start pulling on that string, Michael, and the string gets longer and longer and longer, and these new issues crop up. But that's where, you know, we as humans have this incredible ability to innovate, be creative, and I can't explain it, but solutions just come out of the universe. They just, you know, it's like there's that universal mind or whatever, and it just, you know, when an idea is needed, boom, it ultimately gets there if human thinking is focused on the problem. So yeah, filters are a problem. What do we do with them?
You know, there are a lot of interest and questions regarding your living walls and living roofs. And so, you know, one question came up from Eugenia, and she said, well, does it have to be mowed? And I'm sure that's all dependent on the type of plants you put up there.
It is. Howard Garrett and I experimented. He did over his office in the back of the house, he did an office master bedroom. He did a soysa grass roof. And he chose not to mow it, and you didn't have to. But no, you don't have to mow a living roof. It comes down to plan choices. On that Plano Environmental Learning Center, I have a living roof on half of that building. And when we did that, there was a consultant that we engaged, and all he kept talking about were using sedges. Mm-hmm. And I was like, you know, I mean, yeah, I get that, but it doesn't seem like we need to do it. I mean, this is, you know, it's called extensive or intensive. The Clyde Warren Park downtown, that's a intensive living roof where it's deep enough to grow trees, and extensive is only about 6 to 8 inches of it's not even dirt. It's vulcanized shale. Okay. And so it's a shallow root system. Well, you know, there are a lot of native grasses and native plants that have shallow root systems. So I planted that roof in natives. And it was kind of a stealth approach, because I wanted to introduce grasses and wildflowers up there that would regenerate. I mean, we've had a fairly good amount of success with regeneration, but there is some manual reseeding that has to be done. But it's a garden. I mean, it is a roof. You can't just do it and forget about it. I mean, you still got to walk through the garden, and you got to pluck a few weeds, and you got to do what you need to do. But the interesting thing about that roof was the only maintenance is they do cut it. They cut the dead grasses down in the wintertime and wildflowers. And all around that center now, if you go and you walk around the car lots, the new car lots, you know, some of the buildings, the other buildings that are around there, if you look along chain link fence, or you look in some of the flower beds or planting beds, you'll see little blue stem, big blue stem, switchgrass, you'll see sea oats, you'll see wildflowers that are coming up. So in a stealth way, we sort of introduce those native species back into the environment simply by growing them on the roof of that building. So doesn't have to be, but it does require maintenance. You have to realize that, just like I said, in your yard, you get invasives, you get, you know, plants die, plants go dormant, you have to remove that. So yeah, you have to be a gardener. You got to maintain, you got to garden your living roof, but you don't have to mow it. Yeah.
Well, landscape is a living thing, and it's not just one thing. It's a mixture, right? I mean, all this monoculture with having the same type of grass just doesn't make sense, because that's not nature. No, it isn't. Melissa asked a great question regarding the living roofs as well, and what she asked was orientation. But the second thing is this more? You've talked about the roofs down here, but is it more? Does it depend on the temperature zone? You know, is it more viable in a temperate zone versus down here in the South, where it's hotter in the summer and more intense?
No, but again, it's all about responding to your regional climate. Chicago has a huge mandate for living roofs. They're trying to make every building in downtown Chicago have a living roof, and they're to a large degree they're making it happen. You go to New York's High Line. I don't know if anybody listening has ever visited the High Line in New York. It was an old railroad line that ran through all of southern Manhattan. And what it was primarily meat. They moved meat to the meat packaging plants. Well, that all ended. And so now you've got this huge elevated steel railway running through that part of the city. Well, what they did with the High Line project was they created a living garden. So now this entire rail line is a garden suspended in the air, and you can walk. They've got walking paths. It's beautiful. It's an elevated park, and so it is like a living roof. And the plants there are very different than what we would use here because it's colder. They have winter, a lot more rain, a lot more temperate than we are here. So the plants are very the plants were chosen for that environment. They were native indigenous kind of plants. So if you're in Arizona, yeah, you can still do a living roof in Arizona. It's going to be a lot of desert flora. Here in Dallas, there's a lot of things we can do. The big issue is water. So in Chicago, New York, they don't have to water those roofs. My living roof in the Plano Living Environmental Learning Center, we have to irrigate because we've only got 8 inches of that shale. And so what we did is we captured, and I didn't really get into this, it's because it's such a difficult thing to do. Not totally difficult, but it's challenging. We capture rainwater off those roofs where the solar panels are. So we capture every drop of rainwater that falls on that building. That captured rainwater is used for 2 things. One, we use it for flushing the toilets and in the urinals. And then supplementally, we use it to irrigate the living roof. So if we were to just plant those wildflowers and native grasses, they die, they burn up. So we had to irrigate that one. One of the reasons they use a lot of those sedges is they go dormant in the heat and then they come back. But even those can burn out. So when you've got a very hot climate, I haven't experimented yet with sort of doing like a desert environment up there. I just do a lot of things like succulents. But yeah, you have to temper the plants to what the environment is up there. In this case, when we use the recycled rainwater, it's great. We just got a drip irrigation system up there, and that's really a no-brainer. So again, when you start pulling the string, when you put a drip irrigation system on a roof like that, you get evapotranspiration, which again offsets even more heat from the roof. So there are more benefits. And the little bit of energy to run the pumps, well, it's a solar-powered pump. So there isn't any energy load that we're dealing with there. So it's kind of fun, really. So when I say pulling the string, you can pull the string to identify problems, but you can also pull that string and you can find a lot of opportunities. So as I said in the beginning, the challenges and opportunities to cross this great divide.
Gary, your living walls also generated quite a bit of interest. One question was whether the living wall in slide 62 was irrigated, but also a lot of questions about bugs, ants, and how those are managed on where you have living walls inside a building. Okay, so same thing. They require maintenance. They do have irrigation. Not a lot of irrigation, but they do have irrigation. They have to be, generally they have to be misted. Bugs are just like anything else. I mean, any building that humans occupy, there are going to be bugs. There's going to be ants. There's going to be flies. There's going to be, water bugs, roaches, all those kind of things. So bugs are part of our biome. We cannot not live without bugs in our biome. But they, again, there are numerous ways to treat those. And again, as you maintain that wall, which has to be maintained, just like with living roof, you can't just do it and forget about it. It requires a gardener. And as a gardener, yeah, you have to address things like, they're ants, who knows where they come from, but they're amazing little creatures and they show up. And,
they like water.
They like water. And so, yeah, and so you have to treat the infestation. And it'll happen. I mean, even in the cleanest, at 1808, we had a big ant infestation. And it's like, where'd it come from? Everybody's like, well, how do these ants get in here? We clean this. We're fastidious about keeping the kitchen clean. I said, yeah, you all are. But you know what? An ant can find, that ant probably came from 100 yards behind this building, got up to the building, followed that edge where it's nice and moist, where the building meets the soil, all the way down, found a little crack through that 18-inch thick concrete foundation, came inside, and now they've got a pheromone-laden trail, and they put the word out, come on, boys, we're home free. There's good stuff in here, and here they come. So, yeah.
Hey, we had a couple more questions on roofing, and as far as on existing residential roofing, the effective or most cost efficient ways to replace that roofing and to insulate it and things like that. You mentioned a couple of items as far as, you know, under the roof insulation products as well as above the ceiling insulation. Do you have any comments on that? There's also colors. I have a standing seam Gavaloon metal roof, but when I did this, I had the option. Mine is silver, so it's reflective, right? But I had the option to buy a white one, to a green one, to a red one, you know, and I'm just wondering if they have the same effectiveness as far as cooling the roof down. We had another question on skyscrapers. What's your opinion on skyscrapers or tall buildings? You know, what do you consider a skyscraper? 5 stories and higher, and what's your idea on that? So if you could address the roofing thing, that'd be great.
Let's talk about the roof. One of the first things we've got to do is get rid of asphalt shingles. You know, this is energy, and it's also environmental. Everybody heard the story about Shingle Mountain and moving that mountain, and there's a lot of controversy about that. And the property was zoned to store those shingles, the shingle waste on the roof. The original landowner, his contract said he would recycle it. He never did. He just piled it up. The folks that lived there bought that land knowing that that was zoned for heavy industrial. That's why it was so cheap that they got that land, because it was, you know, right next to the landfill. It was zoned for uses like, you know, all kinds of nasty uses. So part of that's bad on them. You know, you're gonna buy a piece of property that's in the floodplain, you know, you're gonna flood. You buy a piece of property in a heavy industrial zone, you can bet there's gonna be heavy industry around you. But point being is that all those shingles, we create a shingle mountain every week in Dallas, all over the Metroplex. We create a shingle mountain because what happens is those shingles volatilize. The thing that makes the shingle flexible are the volatiles from the petroleum, the fossil fuel that goes into making those shingles. Once that shingle loses all those volatiles, it becomes brittle. It used to be called a coal tar roof. You put it down, it's real nice and flexible. It's black. You've seen them. They use it in the 50s a lot. But after about 10 years, they get brittle. That coal tar gets brittle and cracks, and it no longer is a viable roof. Well, the same thing happens with shingles. And when you hear about all these roofs being replaced in hailstorms, it's because the volatiles are gone. All that nasty stuff, benzenes, toluenes, all that nasty stuff that comes out of petroleum has volatilized and gone into the atmosphere. Great, right? So we're breathing all that. But then on top of that, then when that shingle loses all the volatiles, becomes brittle, now again, it's just a thermal heat sink. It's black, it's just absorbing heat, and it's driving that heat into your home. And then you have to scrape it off, and that's how we get a shingle mountain every week. So shingles are just bad. There's no other way to describe it. Shingles are horrific. The only thing about them is they're cheap, and that's why people do it to put on their roofs. What you did with your Gavaloon roof is that has high emissivity, high reflectivity. It's the best way to do it. And if you create a little 1/2-inch airspace underneath it, it's even more effective, because then it creates a thermal siphon where hot air collects that heat out of that metal and takes it up to the ridge and gets rid of it. Whether you paint, the painted ones, white, green, all those other colors are great. They've got the new cardar coatings are lasting much longer now, 25, 30 years. And all that'll happen is the paint will fade, but the aluminum metal roof underneath there will last, 100 years or more. So it'll still perform. Interesting point, green, the color green makes sense when you think about this, right? Green is the most efficient reflective surface. So green, the color green reflects more radiated or direct energy from the sun than any other color, including Gavaloon. And I was like, huh. Then I thought, oh, that makes perfect sense. Look at the earth. So,
yeah. But metal roofs are very expensive. And so what is a cost effective for replacing a roof that's not shingles?
Metal roof is really the only way to go. I mean, it really is. I mean, you can do the concrete tile roofs, or the clay tile roofs. They're very expensive, or the concrete or slate shingles. That's all incredibly expensive, and there's real benefit to those. But the thing is, what you have to realize is if you do a metal roof, you're going to automatically get a 25% discount on your homeowner's insurance if it's a minimum of 24 gauge, because it's hail resistant. So when you put a metal roof on, okay, it's going to cost three times perhaps more than a shingle roof. But now 25% of that cost is offset by your savings in your insurance. On top of that, you put that metal roof on, you're done. You know, that's your lifetime. That whole roof is going to last your lifetime. In Dallas, shingles are replaced every 3 to 5 years. So when you think about being in a house for 15 or 20 years, think about that. So yeah, it's cheap. Guess what? You better save some money in three to 5 years. You know, and yes, insurance companies are starting to move away from complete replacement at no cost to you. And how they're doing that is the insurance rates keep getting jacked up. I have to fight my insurance company every year and say, whoa, wait a minute. I'm not paying that rate. I have a metal roof. Why am I paying to help offset the cost of these stupid shingle roofs? So I have to fight that battle every year. But yeah, so a metal roof is, yes, but like anything else, solar's not free. If you're going to put PV panels on your house, there's a front end cost. Even though you can amortize it over 3 years, expedited amortization, you can also take advantage of whatever subsidies are available from Encore or whoever, but there's still, you've got to write a check to put those solar panels on your roof. So you're paying forward on your electricity bills to someday when you amortize the cost, then the electricity is pretty much free. But then there's a life cycle to a panel. Right now it's 25 years. If 25 years, those panels sort of lose their optimization and they start to diminish in terms of.
Well, I'll challenge you on that, Gary. And the fact is that it's their production capability is reduced in 25 years. So it doesn't mean that they're not going to last. They're just not producing
no, that's what I'm saying.
efficiently.
That's what I'm saying. That isn't like after 25 years, they're worthless. No, their production starts to diminish.
Now, I do believe they can be repurposed if you want to get more efficient panels, but there's other people like in energy deserts where they could take these other panels and move forward with them.
Replace them and move them somewhere else. But that's the point I'm trying to make is paying forward on your roof is the same as paying forward on a solar panel.
Exactly. And that raises Molly had a great question in regards to, in your practice, you do a lot of design and everything. And you mentioned that this one building, commercial building, did not have solar, or maybe it was a school, because they didn't have the finances for it. But the thing is that did you design it to be, well, what we call net zero or PV ready? So when they do want to go solar, they have the capability, they don't have to, they're ready to go.
Absolutely. I mean, that's standard in my practice. The buildings are designed in a way that we've reduced the demand to the absolute minimum, and they're all set up to be PV solar ready. And so an owner can at any time install that energy, and then they'll be at true net zero. So yeah, no, that's fundamental. Let me go back to one thing, Michael, when you talked, the other piece of that roof equation was insulation. So there are a number of things you can do. There are those paints that you can spray, reflective paints that take a standard tract home. You can spray that reflective paint on the bottom of the roof deck, and they're very, very, very effective. Then you can spray foam. You can spray foam insulation to the underside of the rafters, or you can spray it on top of your ceiling. Most people don't like to do that on the ceiling because if you ever have to chase a leak or replace a drywall, it's kind of difficult. You can use bad insulation or the blown-in bibs, but if you can get your attic conditioned and get that up to an R42 to R46, which you can do after the fact. It's a retro kind of thing. It's something you can do in an old home or a new home, but you get that insulation up there. That the benefits from that are huge. My son bought an old home, and we're going to ultimately do a full roof reno, metal roof. We're going to do foam on the underside of the rafters, but just to get him started, it only had about 3 inches of insulation in his attic on top of the ceiling. So we blew in 25 inches of blown in bibs, and it cut his heating. I mean, he said he hardly ever noticed the furnace coming on, and his cooling has been substantially reduced to almost, his bills are nuts. It's only like he's paying $35 to cool his house. So we did that knowing full well that insulation is there, and it's going to settle and it's going to change. But we're talking about when we re-roof, we may still do the foam. But so insulation is key to any of those roofs, but getting rid of the dark shingles and insulation is the best thing you can do.
So Tracy just asked, what's a blown-in bib? And then I'll go back to the skyscraper question. If you could answer that.
Yeah. So what was the question?
Blown in bib.
Yeah, blown in bib. It's like a chopped up fiberglass. I don't like cellulose for a lot of reasons, but the blown in bibs is it's blown in. I think originally it meant blown in bats is what it was. But
Yeah.
It's like chopped up fiberglass. I'm kind of, there's the jury's out on fiberglass. I think the little fibers kind of concern me. It's long glass fibers, not short fibers like asbestos, but anything fibrous like that still gives me the heebie-jeebies. And
Do you ever work with mineral wool as an insulator?
We have, and it's, it's fine. It's just that I don't use it because foams are far more efficient, closed cell and open cell, and they both have additional benefits that the mineral wool does not. So I just tend to use, I get more bang for the buck out of the foams.
Okay.
So high rise. So the question is, what was the question about high rises?
What's your opinion of them? I mean, as an architect, I guess, as far as how they can become more energy efficient, or what are the issues with high rise buildings?
Well, we talk. I'm gonna talk. This is more theoretical than anything else, but high rises are great in that you use very little. You can have a higher density of occupied space in a smaller area. So instead of, Wright wrote that book called The Living City. And his idea was that there would be no building taller than four stories tall. But the problem was, it becomes this sprawling, metropolitan, mega suburb with more roads and more transportation. Where when you do a high rise, you can design your transportation efficiently, and you can get a lot of people working in a building that requires very little land mass. And in terms of the efficiencies of the building, yeah, absolutely. I mean, you've got a very tall building, so one of the advantages you've got is that thermal stack effect, which can be used to great advantage to move air in a building naturally and move it between the floors, and just wonderful opportunities with a high rise that you don't have with a low rise. So no, I'm not opposed to them at all. I think we have to pay more attention, which we are starting to do in cities, in terms of sunlight corridors and wind and those sorts of things. But again, that's a design problem and not an environmental problem. So I don't really have an issue with skyscrapers as long as we think about the glazing systems and we think about those view corridors and sun corridors and the wind and they really offer tremendous opportunities to heat and air condition them naturally.
Gary, do you have a couple more minutes to spend with us?
Yeah.
There's a couple more questions that have come in asking about the foam insulation, as far as, what's the lifetime of the foam that, you're working with? And then what about outgassing of formaldehyde, or maybe that's not a problem with the foams you're using or recommending?
There's no problem with off-gassing anymore. I mean, Icynene was one of the first that virtually had no off-gassing issues. And now, now the soy-based, they're all so clean that the blowing agents are clean. There really isn't any off-gas issue anymore. Now, are there some foam companies out there that have some issues? Yes. They've been minimized, certainly. But to a large degree over the past 2 decades, off-gassing, there's no formaldehyde used in spray foams I use. The Icynene and the soy-based foams, there's no formaldehyde. And there's no toxicity in terms of benzene, toluene, all that sort of thing. The reaction agents now are carbon dioxide. So as soon as those foams are sprayed in liquid form, they react with the natural carbon dioxide environment,
yeah.
and boom, they foam up.
Is there a life cycle? I mean, as far as expected, life, do they deteriorate over time?
Way beyond our lifetime. It's way beyond our lifetime. So that's not even an issue. And there are 2 types. There are closed cell and open cell. Open cell can have issues with the presence of water, liquid water, because they're based, they are hydroscopic. Moisture can move through them. But I'm not getting into the technicalities of that, but You just have to think about when you're constructing that, whatever that is, whatever that component is, you have to realize that if there is a great deal of moisture, it's going to get in the building. And the other kind is closed cell insulation, and moisture doesn't move through closed cell. It's not hygroscopic. And the other issue about closed cell is if it's sprayed on the underside of a deck or a roof, it can really preclude moisture infiltration. So leaks.
Yeah. It prevents leaks is what you're saying.
Right.
It's also a fire retardant in a way, isn't it?
Some of them are. Yeah, you have to check which one. Most of them are, but you have to check the fire retardant rating.
There's a question.
This is Rosa. Hold on.
Oh, go ahead.
There was a question earlier on about those liquid-filled columns that you showed in one of your slides.
Right.
There's a question from Eugenia about how they work, how common they are, and how cost-effective.
Well, you don't see them much anymore. They were all the rage, like I said, at the time, I built trum walls. I never had the chance to build a water one. But effectively, you're building these columns. They're like aquariums. I mean, so there were some people even did aquariums, that kind of thing. But you know what happens to water if it's not sealed properly? It'll go stagnate and it'll change color. And if there's any organic material in there, it'll fill up with algae. But the concept was that you had a thermal mass, which was water in those columns. And it's just a trum wall. It's just a thermal mass storage system. So the water would heat up when the sun hit it. And then at night, it would radiate that heat back into space. But when you think about having that much water in columns in your house, great idea. I think it's a marvelous idea. But effectively, I think it was more problem than it was worth. And you just don't see much of it at all anymore. Trum walls are still done. And as I said, the problem with the trum wall is it kills your view. Now, what Emory did at his Rocky Mountain Institute, he didn't need the view where he backed that up because he's got the greenhouse, and they all work and kind of live in that greenhouse. So the trum wall is in there to store the heat, but it's a smarter way to do it. In our climate, trum wall doesn't really make a lot of sense. If you're in a more northern climate, it makes a great deal of sense, but you're offsetting the view. So the water columns, I think they were a great idea at the time. I think they proved problematic because of the seals, and then, draining those things or dealing with that water in the middle of your house was problematic, but interesting, looks fun. I've seen some other ones where they actually created these kind of pillows out of water that were sealed, completely sealed hermetically. And then they stacked the pillows in a rack, and they didn't have as much issue with that because you're only dealing with a pillow of water rather than these big columns of water. And those were interesting. And because of the way they were sealed, there wasn't any problem with the algae or the water going stagnant, that sort of thing. It's kind of like earth tubes. Earth tubes were a real rage back in the 70s. And what you would do is you'd run a tube underground, you'd run a pipe underground, and it would be, you'd run it around the house a bunch of times. And then what would happen was cool air would flow through those earth tubes and come up in the house to cool the house. Well, yeah, it's great in concept, but then people realize that there's something called condensation that happens about halfway down that earth tube, that earth pipe. And when that condensation happens, then you get a mildew or algae bloom, and then guess what? Really stinks. So great idea. Everybody, it was all the rage for a while until, hey, we got a condensation issue in the tube. It isn't like you can just deal with the condensation at the other end. It's right in the middle of the tube where you can't get to it. So, sometimes good ideas make a lot of sense, and you either pursue the technology a little longer and realize, well, maybe this is more work than it's worth.
There's a question about what do you think of boxable, which is something I'm not familiar with. And then do you have for a residential property, do you know, for a retrofit, about what the cost per square or square foot for a metal, converting to a standing seam metal roof would be?
I'm just not close enough to that because the costs are changing. If I told you a number now, it would either be more or less in the coming months. I mean, we've got this inflation bubble going on right now. So I'm just, you need to, the best way to get that answer is talk to a contractor. Yeah. I don't know what was it? Boxable?
I'm not familiar with who they are or what they are.
I don't know what it is.
Okay.
Rob, that was your question. Do you want to explain what that is? Unmute yourself.
Yes, thank you. Boxable it's a kind of a small prefab house that folds up into a box and then unfolds. And it got some notoriety because Elon Musk bought one for his Boca Chica. You know, it only costs like $50,000 and it has several, I don't know, a few hundred square feet.
Oh, so
yeah,
it's like
transportable, and then you can put it up, erect it in about 3 to 5 hours.
Or minutes, something. Yeah.
I'm curious. I'm gonna look it up. Boxable. That's interesting.
Yeah.
I just figured as an architect, you might be interested.
You know, you see tiny houses everywhere, pre-manufactured housing, all those sorts of things.
Yeah.
But yeah, not
hey, Gary, have you been involved with BIPV? That's solar PV as a part of the vertical structure of a building, a commercial building, like either replacing windows that have PV and can help offset some of the electric load, for lighting and things like that. Have you worked with anything like that?
I've started to look into that. The problem was, the early solar panels were unidirectional, and that's why they were having problems mounting them vertically. But now a lot of the crystalline structure inside the panels are omnidirectional. So as long as there's reflected or diffused light, they can generate power. I haven't really looked at those much yet. I just need to spend some more time to see if they've kind of breached that efficiency curve.
Yeah, there's not a lot of commercial products out there, but there's a lot of technology looking into it. So, any other questions from anyone? All right.
Okay.
Thank you, Gary.
Well, Gary, we can't thank you enough. Terrific presentation. Let's give Gary a good round of applause.
Right.
Thank everybody for attending. We still have most attendees still here. Our next meeting will be on Saturday, August 14th. We're still working on our presenter. Rest assured though that since this was a legislative year, sometime before the end of the year, we will bring you a speaker to bring us up to date on any new laws that have been passed in Texas that may affect renewable energy or sustainability. So thank you all very much. Again, please volunteer and thank you for your participation, at least in the monthly meetings, but volunteer as much as you can. We need your help. We can't do it without you. Thank you much. Have a great time. See you next time.
Yeah, just remember this has been recorded and it will be available from the NTREG.org website to all the members and people who come on. And if you know someone who's interested, please join us. It's only $20 a year. See what you get. Gary Olp. Fantastic.
Thank you.
Thanks everyone for listening. I appreciate it. I hope I inspired a little thought, and let's keep moving forward.
You did. Thank you, Gary.
All right.
Gary,
Rosa, give me a call. I want to talk to you about the mentoring program.
Yes, sir.
We can talk about that offline.
all right.
Absolutely. Thank you.
Gary, I'll follow up with you offline as well in regards to the our CCAP initiative.
That'd be great. That'd be great.
Thank you.
All right.
And with
Thank you,
you,
guys.
Tracy.
Thank you, everybody.
Cheers.
Bye.
Bye.
Michael, do you want to stop the recording?
I will.
I'm listening.
Thank you.